Come on, my dears, let us proceed further in this last chapter. Now, today we will see about speed of transverse wave in the elastic medium. Okay. First of all, let us recall what do you mean by transverse wave. Fine. Just consider a thin string which is kept under proper tension. So, there is the thin string which is kept under proper tension. Now, what we do? We just displace its one of the particles and we just displace it in a direction perpendicular to length of the string. Okay? And then after when we release it, it so happens that that particle starts oscillating in a direction perpendicular to length of the string, and at that time the direction of propagation of wave is like this. Correct? Fine. So, you can see here direction of oscillation of particle of medium and direction of propagation of wave are mutually perpendicular. Then that wave is called transverse wave. Correct? During the propagation of given wave, if particles of medium oscillate in a direction perpendicular to direction of propagation of wave, then that wave is called transverse wave. Correct? So, here the wave propagating in a thin string which is kept under proper tension is found to be transverse in nature. Okay? But now with what speed that wave will propagate, that is what we want to study. Okay? Remember, when you displace any constituent particle of the string from its equilibrium position, then after what happens? It returns back towards its equilibrium position. Correct? But how fast will it return to the equilibrium position? That depends on the elasticity property of the medium. Correct? And one more thing, when you exert here deforming force, then this particle is getting displaced. But how much will be the displacement? That is decided by inertia of the medium. So, there are two properties of medium which affect the velocity of propagation. They are elasticity and mu, that is measured by inertia. That is measured by inertia. So, there are two factors which decide the value of velocity of propagation of transverse wave in the elastic medium, and those two factors are two properties of that medium. One is called elasticity and another property is called inertia. Okay, fine. Now, at present we are supposed to derive the formula for velocity of transverse wave propagating in a thin string which is kept under proper tension. Okay, fine. Now, suppose that velocity is v, we will obtain its formula using dimensional analysis. Fine. First of all, let us define what is called linear density of mass. Linear density of mass for the string is shown by symbol mu, and it is a ratio of total mass of the string divided by total length of the string. Total mass of the string divided by total length of the string. Okay? And whenever you have ratio, how do you define it? Taking denominator as 1 unit. So, this linear density of mass is nothing but mass per unit length. Mass per unit length. Correct? Mass of a string per its unit length is called linear density of mass for that string. Correct? So, in short, it is total mass upon total length. Unit wise you can write kilogram upon meter. Kilogram upon meter. What about dimensional formula? Come on, dimensional formula for mu will be, for mass you know it is m raised to 1, for length L raised to 1. So, take it up, m raised to 1, L raised to minus 1, T raised to 0. M raised to 1, L raised to minus 1, T raised to 0. Correct? Fine. Now, when we want to obtain the formula using dimensional analysis, we have to assume the dependent factors which affect the value of velocity. Correct? Now, come on, this velocity is found to be depending on linear density of mass, that is on mu. But how is the relation between V and mu? At present we don't know. so we just assume the power as A. Similarly, this velocity depends on the tension produced in the string shown by symbol capital D, but how is the relation between V and T? At present we do not know, so we just assume the power to be small b. So this velocity of propagation of transverse wave in an elastic medium is directly proportional to mu raised to A, directly proportional to T raised to B. Okay, just be careful, this capital T is not temperature, it is tension produced in the string. Take care. Now for the combined dependence, what you should do on the right hand side? Multiplication. So V is proportional to this into this, mu raised to A, T raised to B. Remove this sign of proportionality, put proportionality constant capital K, mu raised to A as it is, T raised to B also as it is. Give it equation number 1. What is capital K? Dimensionless proportionality constant. Dimensionless proportionality constant. And A and B belong to R. Values of A and B we have to find out using dimensional analysis, and value of K is to be determined practically. Got it? Fine. Now just write down dimensional formula on both the sides. For velocity, don't you know? It is m raised to 0, L raised to 1, T raised to minus 1. Just check it. M raised to 0, L raised to 1, T raised to minus 1. Correct? Come on. For K, because it is dimensionless, you don't have to write anything. What about mu? Dimensional formula for mu, we know it is m raised to 1, L raised to minus 1. Correct? If the power is 0, if you do not write, will do no problem. You simply write m raised to 1, L raised to minus 1. Here it is, m raised to 1, L raised to minus 1. Correct? Whole raised to A, don't forget this power, into T raised to B. But what is capital T? Tension produced in the string, which is some sort of force. And for force, what is the dimensional formula? M raised to 1, L raised to 1, T raised to minus 2. M raised to 1, L raised to 1, T raised to minus 2, whole raised to B. Correct? Fine. Now this left side as it is, m raised to 1 into A, that is A, m raised to 1 into B, that is B, then m raised to A into m raised to B. How much it is? M raised to A plus B. Here it is, m raised to A plus B, L raised to minus 1 into A, that is minus A, 1 into B, that is B, L raised to minus A plus B now, L raised to minus A plus B. Correct? When bases are same, then you can make addition of powers. Come on. T raised to minus 2 into B, T raised to minus 2 into B. Got it? Fine. Now just compare the powers to the base T. Correct? Powers or dimensions with respect to time, they are minus 2b here and here minus 1. So when you compare, minus 2b equals to minus 1. Minus 2b equals to minus 1. Naturally minus minus will become plus. B equals to 1 by 2. B equals to 1 by 2. Correct? Compare the dimensions with respect to mass. Here it is A plus B. Here it is 0. So A plus B equals to 0. And then value of B is 1 by 2. Put B equal to 1 by 2. Correct? Transfer this. From plus it will become minus. Correct? A equals to minus 1 by 2 and B equals to 1 by 2. Just put the values in this equation number 1. Come on. A has come out to be minus 1 by 2 and B has come out to be plus 1 by 2. Correct? Fine. Now this mu raised to minus 1 by 2, if you take it in the denominator, it will become mu raised to plus 1 by 2. So it is T raised to 1 by 2 upon mu raised to 1 by 2, that is T upon mu whole raised to 1 by 2. Correct? And now K as it is, and when the power is 1 by 2, it is as good as taking the square root. So it is K into under root of T upon mu. Fine. Value of K is determined experimentally, and it is found to be in this case K equal to 1. Just put K equal to 1 here, then V equals to under root of T upon mu. V equals to under root of T upon mu. Got it? Tell me, this is the formula for finding velocity of transverse wave in the elastic medium. Got it? And you can see from the formula, this velocity depends only on two factors: tension produced in that string or in the wire, means in the one dimensional medium, and this mu is linear density of mass. Correct? This velocity does not depend on frequency, does not depend on amplitude of the wave. Okay, I repeat, this velocity does not depend on frequency, does not depend on amplitude. Okay, same thing I have written here. Above speed does not depend on frequency or amplitude. Got it? Fine. Now kindly read the statement of example number 6, illustration number 6. Have you read it? Fine. We have some rigid support here, with the help of which we have suspended a series connection of two wires. One is from P to Q, another is from Q to R. This is wire number 1, this is wire number 2. Fine. Now tell me, because it is a series connection, remember, in case of series connection, when you just make this series connection loaded by some weight, then you are exerting external force vertically downwards this way, correct? And then in just opposite direction, you will have same tension produced in both the wires. So here also it is T, here also it is T. The amount of tension produced in both the wires is same because they are connected in series. Okay, fine. And now, what about linear density of mass for first wire? Let it be mu1. Then according to definition, it is total mass upon total length. For the first wire, it is m1 upon L1. Correct? This mass of first wire, they have given 0.06 kilogram. Length of first wire, they have given 4.8 meter. Simplify. Answer is 1 upon 80. Unit of mass is kilogram. Unit of length is right now meter. Correct? Similarly, we can find out linear density of mass for second wire. Mu2 equals to m2 upon L2. m2 upon L2. What is mass of second wire? They have given in the statement 0.2 kilogram. Length of second wire is 2.56 meter. And now this answer is 10 upon 128 kilogram upon meter. Correct? Fine. And now tell me, V equals to under root of T upon mu. Just now we have found out the formula. V equals to under root of T upon mu. But because tension is same and constant here, then T is constant. And for the first wire, when you write here mu1, here you should write V1. Correct? Let us find out under root of T. What is T? Tension produced in both the wires. They have given in the statement as 80 Newton. What about mu1? Mu1 we have found out 1 upon 80. Mu1 is 1 upon 80. Simplify, answer is 80 meter per second. Similarly, what is the velocity in the second wire? V2 equals to under root of T upon mu2. What is T? Tension in the wire. They have given in the statement 80 Newton. What about mu2? Mu2 is right now 10 upon 128. 10 upon 128. Simplify, answer is 32 meter per second. Correct? Wait. Now what have they asked? That when a wave is produced at point P, here at the top end, that wave propagates in this entire length, and then after it comes at the bottom end. Okay? But for that, how much time is taken by that wave? That is what we have to find out. Find out time taken by that wave which is generated at this top end. When it reaches at the bottom end, how much time is taken? Let us find out. That total time I am taking as T, which you can write as T1 plus T2, where T1 is the time taken by wave to travel the length of first wire, correct? T2 is the time taken by wave to travel the length of second wire, correct? But don't you know, constant speed equals to distance traveled divided by time taken. Constant speed equals to distance upon time, then time will be distance upon constant velocity. Distance upon constant velocity. Come on, length for the first wire is L1, constant velocity in the first wire is V1. For the T2 value, you can write similarly L2 upon V2, correct? Time equals to length upon velocity. Time equals to length upon velocity. Simple? Come on. L1 is the length of first wire. They have given in the statement 4.8 meter. Velocity we have found out in the first wire, it is 80 meter per second. What about L2? Length of second wire, they have given 2.56 meter. Velocity in the second wire, we have found out 32 meter per second. 32. Simplify, this answer is 0.14, that many second. Leave proper gap, write small s, don't put any full stop. Got it? Fine. So this much time will be taken by the wave to travel this much distance from this end to this end. Correct? So that time we have found out 0.14 second. Got it? Fine. Read now statement of sum number 7. Read it? Look. Here we have some rigid support with the help of which we have suspended some rope, some thick rope is suspended, and at the lowest end of rope we have tied some block. Suppose mass of this block I am taking as M1 and mass of this rope I am taking as M2. Okay, fine. Now tell me, at this lowest end of the rope, what is being suspended? It is mass of the block, which is M1. Don't you know, weight of any block is nothing but mass into gravitational acceleration. Mass is M1, gravitational acceleration is G. So at this end, the external force exerted is M1 into G. Correct? But now you know, in just opposite direction, you will have restoring force developed, and that restoring force is called tension produced in this rope at this lowest end. Let it be T1. And you know, magnitudes of restoring and external forces are equal. So right now T1 equals to M1 into G. T1 equals to M1 into G. Correct? M1 is mass of the block. They have given 2 kilogram. Leave this G as it is. You may put the value of G 9.8 meter per second square, no problem. But here we don't require to put the value of G. Ultimately is going to be getting cancelled. Okay? Because G value is going to get cancelled, we don't put its value. Come on. Similarly, now tell me, at this top end, what is the total external force exerted at the top end? Come on, weight of the block is already there, that is M1 into G, plus weight of this rope, which will be M2 into G. So the total external force vertically downwards at this top end is M1 into G plus M2 into G. M1 into G plus M2 into G. You can take G common, that is M1 plus M2 into G. Correct? That is total external force vertically downwards, and you know restoring force will get developed just opposite. Then from this end it will be getting developed vertically upwards, and that vertically upward restoring force will be equal to this total external force, which is M1G plus M2G. M1G plus M2G, let it be M1 plus M2 into G. Correct? But that is the restoring force developed at the top end, and that will give you tension produced in the rope at the top end, and let it be T2. Correct? Tension produced in the rope at the lowest end is T1, at the top end it is T2. Come on, M1 is mass of the block 2 kilogram, M2 is mass of the rope 6 kilogram, G as it is. So this is 6 plus 2, that is 8 into G. Leave it as it is. Don't put the value of G. Okay, fine. Now tell me, V equals to F lambda. Velocity of propagation for any sort of wave, you can always write frequency into wavelength. Frequency into wavelength. But right now this velocity of transverse wave in the elastic medium, you know by formula, it is under root of T by mu. So this velocity is under root of T by mu. Correct? Now tell me, for both of these objects, for this entire rope, tell me its linear density of mass. Linear density of mass is same and constant throughout its length. Correct? So mu is constant, and here frequency will remain same. Correct? When the wave is going from here to here, frequency will remain same. Now tell me, when frequency is constant and mu is constant, what is the relation between lambda and capital T? Relation will be lambda proportional to under root of T. Lambda proportional to under root of T. Wait. Frequency of the wave generated at this lowest end is constant. Mu is constant for this rope. When these two are constants, what is the relation between lambda and capital T? Lambda proportional to under root of capital T. Now tell me, is the tension same throughout the length of the rope? No. At this lowest end, it is the smallest, and as you just move this way vertically upwards, and when you reach at the top end, the tension is maximum. Correct? So along the length of the rope, tension value keeps on changing. And because tension is changing, that's why the wavelength will also change. Correct? Fine. That's why we are asked to find out wavelength at the top end of the rope. Okay? When the wave is generated here, by the time it reaches at the top end, what would be its wavelength? We have to find out. Come on, lambda proportional to under root of T, direct proportionality relation, then 1 to. So lambda 1 upon lambda 2 will be equal to under root of T1 upon T2. Come on, lambda 1 is the wavelength in the wavelength of the wave which is produced at this first end. Okay, fine. Now that wavelength they have given in the statement 0.06 meter. Lambda 2 is the wavelength of the same wave when it reaches at the top end. That is what we have to find out. Under root of T1 upon T2. T1 is the tension at the lowest end and it is 2 into G. 2 into G. And what about T2? T2 is the tension at the top end which is 8 into G. Come on, T2 is 8 into G. Correct? Now GG will cancel. Correct? 2 4s are 8. Its square root will be 1 by 2. Take this 2 here. 0.06 into 2, that is 0.12, that many meter. Correct? So this must be the wavelength of the wave when it reaches at the top end. Got it? Fine. Read now statement of sum number 8. Read it? Come on. V equals to under root of T by mu. Correct? Then take square on both the sides. So V square will be, when you take square, this square root will vanish, giving you T upon mu. Now T as it is. What is mu? Linear density of mass, and it is total mass divided by total length. Total mass divided by total length. Come on, M upon L. Denominator will become numerator. So T into L upon M. And now find out tension in the wire. Just make it subject of the equation. Transfer this M here, transfer this L in the denominator. So T equals to mv square upon L. mv square upon L. What about mass of the wire? They have given 5 gram. Convert gram into kilogram, multiply by 10 raised to minus 3. Then V is the velocity of propagation of wave. They have given 80 meter per second. It's a square. Divided by length of the wire, they have given 50 centimeter. Convert into meter, multiply by 10 raised to minus 2. Simplify. This value comes out to be 64 Newton. 64 Newton. Fine. Then recall the formula for Young modulus. Formula for Young modulus was ratio of, come on, longitudinal stress upon longitudinal strain. Longitudinal stress upon longitudinal strain. And you know this Young modulus is elasticity constant pertaining to length. Then you may define it this way also. Tensile stress upon tensile strain. Correct? What was tensile or longitudinal stress? It was restoring force per unit area. That is total restoring force upon total area. And tensile strain was change in length upon original length. Correct? Fine. Now here this restoring force developed in the wire is nothing but tension in the wire. tension in the wire. So F is right now capital T. So I am just replacing F by capital T. This A will come down and L will go up. So it is T into L upon A into delta L. A into delta L. Correct? This is tension in the wire. This L is original length of the wire. Delta L is the change in length of the wire. A is cross sectional area of the wire. Got it? Fine. And now what about T? Tension. Come on. That tension we have found out, it is 64. Correct? Now just find out delta L from here. Make subject of the equation delta L because we want to find out change in length of the wire. Find out delta L, it will be T into L upon A into Y. T into L upon A into Y. T into L upon A into Y. Correct? What about tension? We have found out it is 64 Newton. T is 64 Newton. What about length of the wire? They have given in the statement 50 centimeter, converted into meter, multiplied by 10 raised to minus 2. What about Young modulus? They have given 16 into 10 raised to 11 Newton upon meter square or Pascal. What about cross section area? Take care. I think in the Gujarati medium they had made the mistake in the printing mistake. In the unit of area, they had written in the Gujarati medium A equal to 1 millimeter. It's not proper. It should be 1 millimeter square. 1 millimeter square. Correct? Come on. Cross section of the wire, they have given 1 millimeter square. If it is millimeter, just make the correction. It is millimeter square. 1 as it is, but 1 millimeter is 10 raised to minus 3 meter and it's a square. Fine. And now tell me, this cross section area, as I said, it is 10 raised to minus 3, it's a square. 10 raised to minus 3, it's a square. Millimeter to meter, you must multiply 10 raised to minus 3 and it's a square because it is millimeter square. So you should write here 10 raised to minus 3 meter and it's a square. And now simplify this delta L, you will get 2 into 10 raised to minus 5, that many meter. Because you are placing all the values in SI unit, naturally this change in length will be obtained in meter. Purposely, if they ask to find out in millimeter, you know 1 meter is 1000 millimeter. 1 meter is 1000 millimeter. So you can multiply here by 1000, it will be 2 into 10 raised to minus 2, that is 0.02 millimeter. That is the answer they have given in the textbook, correct? 0.02 millimeter. But unless asked to find out in millimeter, you should not go for it. You should find out only in meter, that will do because it is SI unit. Fine. Now in further topic, we require 2 results to be utilized. So better we should prove those results first. Okay, I am showing you 2 proofs. One of the proof is this. Show that B theta equals to P. B theta equals to P. But what is B theta? B theta is called isothermal bulk modulus. Isothermal bulk modulus. And it is shown by symbol B theta. And that is what we have to prove to be equal to pressure. Okay. How to prove? I am showing you. Recall the formula for bulk modulus. We had studied earlier in the chapter of elasticity, and that formula was minus dP upon dV upon V. Minus dP upon dV upon V. Minus dP upon dV upon V. Fine. But because this bulk modulus is right now found out keeping temperature as constant, then we call it isothermal bulk modulus. We show it by symbol B theta. Fine. Tell me for isothermal process, don't you know the relation between pressure and volume? What is the relation? P into V equals to constant. P into V equals to constant. Take d by dV on both the sides, that is derivative with respect to volume. Derivative with respect to volume I am taking on both the sides. Come on, how to take derivative of a product? Don't you know the rule? Rule is that first function as it is into derivative of second function plus second function as it is into derivative of first function. Come on, follow the same rule here. First function as it is, so P as it is, d by dV of V is 1 plus second function as it is and into derivative of first function, that is dP upon dV. dP upon dV. And derivative of a single constant term is 0. Now P into 1 is P, and transfer this term on right hand side, from plus it will become minus. Minus V dP upon dV, minus V dP upon dV. And now this V I can transfer in the denominator's denominator, okay? And then you will find it like this, minus dP upon dV upon V, minus dP upon dV upon V. But minus dP upon dV upon V. When the process is isothermal, it is shown by symbol B theta. So this is nothing but isothermal bulk modulus shown by symbol B theta. So this is nothing but isothermal bulk modulus shown by symbol B theta. So what we have proved? B theta equals to P. Come on, B theta equals to P. What is equal to what? Isothermal bulk modulus is found to be equal to pressure. Correct? Fine. Similarly, second result we require to be proven this way. Come on, BH equals to gamma into P. BH equals to gamma into P. BH is called adiabatic bulk modulus. BH is called adiabatic bulk modulus. What is gamma? You must have remembered from the chapter of thermodynamics. Gamma equals to Cp upon Cv. That is ratio of molar specific heat of a gas at constant pressure to at constant volume. Remember, gamma equals to Cp upon Cv. And what is P? Again, pressure only. We have to prove that BH equals to gamma into P. Come on. This is bulk modulus. Its formula is minus dP upon dV upon V. But when you are talking about adiabatic process, just recall the relation between pressure and volume for adiabatic process. Relation between pressure and volume for adiabatic process, it is P into V raised to gamma equals constant. P into V raised to gamma equals to constant. Take d by dV on both the sides. Come on, here also d by dV, here also d by dV. Fine. Now how to take derivative of a product? Just now I told you, first function as it is into derivative of second function plus second function as it is into derivative of first function. Come on, P as it is, d by dV of V raised to gamma. D by dV of V raised to gamma, it is gamma into V raised to gamma minus 1. Come on, d by dx of x raised to n. Remember, n into x raised to n minus 1. Like that, d by dV of V raised to gamma, it is gamma into V raised to gamma minus 1. Fine. Now V raised to gamma as it is, and derivative of first function, come on, dP upon dV. V raised to gamma as it is, dP upon dV. And that equals to, come on, derivative of a single constant term is always 0. Now this part I have written as it is. I have divided all the terms in this equation by V raised to gamma minus 1. Divide all these terms by V raised to gamma minus 1. Divide by V raised to gamma minus 1. And 0 upon anything will remain 0. Now come on, V raised to gamma minus 1, V raised to gamma minus 1 getting cancelled. Left is gamma into P, gamma into P. And come on, when you take this term in the numerator, this power will be, the sign of the power will get reversed. Now it is V raised to gamma into V raised to minus gamma plus 1. V raised to gamma into V raised to minus gamma plus 1. Base is same, addition of powers. V raised to gamma minus gamma plus 1. V raised to gamma minus gamma plus 1. Gamma minus gamma will cancel. V raised to 1, that is V. Correct? I am writing here V. Correct? Once again, take this up. From power gamma minus 1, it will become now minus gamma plus 1. V raised to gamma minus gamma plus 1. Gamma minus gamma will cancel. V raised to 1, that is V. Okay? This dP upon dV I have written as it is, 0 also as it is. And now transfer this term on right hand side. From plus it will become minus. And now take this V in the denominator's denominator. So it will appear minus dP upon dV upon V. Minus dP upon dV upon V. Tell me, what is this? Minus dP upon dV upon V. It is BH. Why it is not B theta? See, same formula here also we are writing, but here we write B theta and here we are writing BH. Why so? Here we were talking about isothermal process. At that time we started with this formula, P into V equals to constant. Here we are talking about adiabatic process, in which we had started with this formula. Correct? So right now right hand side must be same. Here these two right hand side values are same, but they are showing you different bulk modulus. This is showing you, come on, isothermal bulk modulus, and this is showing you adiabatic bulk modulus. Correct? Fine. Don't go for the formula, I mean the expressions. Expressions you may find same, but the values are different here. Correct? That's why I am giving different symbol. Here I am giving symbol B theta, here I am giving symbol BH. Wait. So in place of minus dP upon dV upon V, I can write BH. In place of minus dP upon dV upon V, I can write BH. Correct? So BH equals to gamma into P. BH equals to gamma into P. BH equals to gamma into P. Correct? What is BH? Adiabatic bulk modulus. What is gamma? Cp upon Cv, P is pressure. Okay, we will use both the relations. Okay, then we go for speed of longitudinal sound waves in the elastic medium. Speed of longitudinal sound waves. Okay, when the sound waves propagate in air or gas, they propagate through longitudinal waves. Okay, during the propagation of longitudinal waves, what happens? You know, condensation and rarefaction takes place. During condensation, the pressure and density increases, and during rarefaction, pressure and density decrease. Okay, and because the change in pressure is occurred during the propagation of such wave, we call such waves as pressure waves. We call them pressure waves. Fine. Now, what is the velocity of propagation of longitudinal waves of sound in air or gas? Let us find out using again dimensional analysis. Fine. Now, here we find that velocity of longitudinal sound waves in air or gas is depending upon the elasticity constant of that medium, and it also depends on density of that medium. When I say only density, you must understand volume density of mass. Okay, if it is linear density, they will specify. If it is surface density, then also they will specify. But whenever we say in practice only density, we mean to say volume density of mass. Got it? Fine. This velocity depends on two factors, elasticity constant and density. But at present, we don't know the powers. That's why we assume the powers to be respectively A and B. And now tell me, as a combined dependence, what you will write? Take the product on right hand side. So V proportional to E raised to A into rho raised to B. Remove this sign of proportionality, put some proportionality constant capital K. Just give it equation number 1. This capital K is dimensionless proportionality constant whose value is to be determined experimentally, and values of A and B belong to R whose values we have to find out using dimensional analysis. Come on, write dimensional formula on both the sides. For velocity, how much it is? M raised to 0, L raised to 1, T raised to minus 1. Velocity, M raised to 0, L raised to 1, T raised to minus 1. K is dimensionless, so we don't have to write anything for that. Come on, E is elasticity constant, and there are three types of elasticity constant. One is Young modulus, another is bulk modulus, third one is modulus of rigidity. Okay, all the three have dimensional formula same as that of pressure. What is the dimensional formula for this elasticity constant? That is for pressure, and for pressure, don't you know? M raised to 1, L raised to minus 1, T raised to minus 2. M raised to 1, L raised to minus 1, T raised to minus 2. Here it is. Come on, for E I am writing here M raised to 1, L raised to minus 1, T raised to minus 2, and whole raised to A. Don't forget this power. What about volume density? It is mass upon volume. So it is M raised to 1 upon L raised to 3. Take it up, L raised to minus 3. So M raised to 1, L raised to minus 3, whole raised to B. Correct? Fine. Now this left side as it is, M raised to 1 into A, that is A, 1 into B, that is B, M raised to A into M raised to B. Base is same, addition of powers, M raised to A plus B. L raised to minus 1 into A, that is minus A, L raised to minus 3 into B, that is minus 3B, L raised to minus A minus 3B, L raised to minus A minus 3B, T raised to minus 2 into A, T raised to minus 2 into A. Correct? Fine. Now just compare the powers on both the sides with respect to time. Come on, here it is minus 2A, here it is minus 1. Minus 2A equals to minus 1, minus minus becomes plus. So A equals to right now 1 by 2. And now when you compare the powers with respect to mass, here it is A plus B, here it is 0. Compare, A plus B equals to 0. Put value of A, which is 1 by 2. Put A equal to 1 by 2 plus B equals to 0. Find out B, it will be minus 1 by 2. A equals to 1 by 2, B equals to minus 1 by 2. Put both the values at a time in this equation number 1. Start with this, V equals to K into E raised to A. V equals to K into E raised to A. A value has come out to be 1 by 2 into rho raised to B. But value of B has come out to be minus 1 by 2. Correct? Now tell me, K as it is, E raised to 1 by 2 as it is, but take this part in the denominator. With power from minus it will become plus. So E raised to 1 by 2 upon rho raised to 1 by 2, that is E upon rho whole raised to 1 by 2. Wait, value of K when determined experimentally, in this case also it comes out to be equal to 1. Put K equal to 1 and instead of power 1 by 2, you may write the sign of square root. So V equals to under root of E upon rho. Come on, instead of power 1 by 2, we are writing sign of square root. V equals to under root of E by rho. Wait, this is the formula for finding velocity of longitudinal sound waves propagating in that elastic medium having elasticity constant as E and having volume density of mass as rho. Correct? Fine. Now, these sound waves are also called pressure waves. Because sound waves are also called pressure waves, actually you know what happens during the propagation of sound waves? During the propagation of sound waves, the region of higher and lower pressure and density propagates, correct? And because on a typical region or typical section of the region, if the pressure is exerted, I mean there is increase in the pressure, then there will be condensation. If there is decrease in pressure, there will be rarefaction, correct? So I mean to say, during the propagation of sound waves, continuously on the medium, some deforming force is getting exerted. Fine. And because of that, what happens? Because of the deformation, come on, condensation and rarefaction are taking place. And because of that, the region of higher and lower pressure transmits. It gets propagated. Fine. And then, because of exertion of deforming force, there is some volume stress. There is some volume strain in the medium, and because the stress and strain are produced pertaining to volume, we must use now volume elasticity constant, and that volume elasticity constant is nothing but bulk modulus, correct? So that's why instead of this elasticity constant E, I should write bulk modulus, that is capital B. Fine. Now instead of E, when you write B in this formula, you will get V equals to under root of B upon rho. V equals to under root of B upon rho. Fine. Now tell me, this formula you can apply for any medium, might be solid, might be liquid, might be gaseous medium, correct? This formula you can apply for finding velocity of longitudinal sound waves. But this formula specifically you can apply only for air medium or only for gaseous medium, okay? V equals to under root of B upon rho. What is B? I repeat, it is bulk modulus. It is elasticity constant pertaining to volume. Fine. Now let us go for Newton's formula for velocity of sound in air or in gas. Mr. Newton had simply assumed that in whichever region the sound waves propagate, in that region he had assumed that temperature remains constant. If temperature is remaining constant, then that process can be taken as an isothermal process. If it is really isothermal process, then we should replace this B by isothermal bulk modulus, correct? Shown by symbol B theta. So B should be replaced by B theta. Come on, B should be replaced by B theta. But just now we have proved that B theta equals to P. B theta equals to P. In place of B, according to Newton's opinion, we should write B theta, but value of B theta comes out to be equal to P. In short, instead of B, you must write P. Come on, instead of B, when you write P, the formula will appear V equals to under root of P upon rho. This is called Newton's formula for finding velocity of longitudinal sound waves in air or gas. Let us check whether this formula is correct or false. Let us check. Come on. You know the value of pressure of air at 1 STP. STP means standardized temperature and pressure. At STP, what is the value of pressure? 1 atmosphere, which is 1.01 into 10 raised to 5 Newton upon meter square. Put it here. And at STP, the density of air is 1.29 kilogram per meter cube. Put both the values, you will get the velocity of sound equal to 279.3 meter per second. 279.3 meter per second. This is theoretically obtained value using this Newton's formula. But practically at STP, the velocity of sound in air is found to be 332 meter per second. 332 meter per second, correct? You can see the variation. Variation is very large, and because the variation is very large, we can say this formula must be wrong. There is something wrong in this formula. That's why we are getting, lot of discrepancy in the theoretical and practical result. Okay, fine. So we need some correction in this formula. And when this formula is wrong, we can say process of propagation of sound waves in air or gas is never isothermal. Never isothermal. Correct? We need now some correction in this formula. Okay, Newton's formula is wrong. That correction later on was introduced by Mr. Laplace. He not only had assumed, he had made right argument. He said that process of propagation of sound waves in air cannot be isothermal, because during the propagation of sound waves, that is during the propagation of pressure waves, rarefaction and condensation are going to take place periodically at the same position. At a particular moment, in a particular position, if condensation has taken place, then because of increase in pressure and density, temperature will increase. But at the same position, after half of the periodic time, there is going to take place rarefaction, where pressure and density will decrease, so temperature will decrease. Now tell me, in a given region, if temperature keeps on changing, either it is increasing or decreasing, if it is keeping on changing, when temperature is not constant, you cannot take that process as isothermal. So that process is never isothermal. Fine. And then after Mr. Laplace said that according to me, means Laplace's opinion was that process is not isothermal, but it is certainly adiabatic. Why it is adiabatic? He rightly said that no doubt condensation and rarefaction take place during the propagation of sound waves in air, but they are taking place very fast. So what happens at a particular position, if condensation has taken place, no doubt temperature will increase. But soon after that, at the same position, there is going to take place rarefaction. At that time, temperature will decrease. So earlier, during the formation of condensation, whatever heat is generated, same heat is getting absorbed there only. That heat is not getting leaked outside, in which the sound waves are not propagating. So I mean to say, between the region where sound waves is propagating and the region where sound waves are not propagating, between these two regions, there is no exchange of heat. If there is no exchange of heat, then that process which is taking place very fast, in which there is no exchange of heat between system and surrounding, don't you know from chapter of thermodynamics, such a process is called an adiabatic process. So according to Mr. Laplace, the process of propagation of sound waves in air or gas must be adiabatic. And if it is adiabatic, we must replace this B by, adiabatic bulk modulus. Adiabatic bulk modulus. So in place of B, we should write BH. In place of B, we should write BH. And what was the formula for BH? Just now we have proved BH equals to gamma into P. BH equals to gamma into P. Put it here. In short, B equals to gamma into P. B equals to gamma into P. Put it here. B equals to gamma into P. Correct? And now put up the values here. Value of gamma for air is 1.41. 1.41. What about pressure? Just now I told 1 atmosphere, which is 1.01 into 10 raised to 5 Newton upon meter square. What about density of air? 1.29 kilogram per meter cube. Put up all the values, find out value of velocity of sound waves in air or gas at STP. It comes out to be in air, not in gas. In air it comes out to be here 331.6 meter per second, and that is the theoretically obtained value. And just now I told about the practical value, it is 332 meter per second. You can see this theoretically obtained value is very close to this practically obtained value. Okay, the difference is negligibly small. In short, Laplace's formula is correct. It means to say that process of propagation of sound waves in air or in gas must be adiabatic. It is not isothermal, but it is adiabatic. In the numericals, whenever they ask to find out value of velocity of sound in air or in gas, you must use Laplace's formula, because Laplace's formula is correct formula. Okay, don't use this Newton's formula. Got it? Come on, my dears, now we proceed further. The next article is about effect of temperature on the velocity of sound waves in air. What is the effect of temperature? I am showing you. Just now we had obtained the formula for velocity of sound waves. As per Laplace's formula, it was V equals to under root of gamma P upon rho. Correct? This is Laplace's formula for finding velocity of sound waves in air. Wait, this under root of gamma into P as it is, but don't you know density is mass upon volume? So rho is m upon V. Denominator will become numerator. Come on, under root of gamma as it is, but don't you know according to equation of state for ideal gas, PV equals to mu RT. PV equals to mu RT. So this P into V is mu into R into T, correct? What about this capital M? It is total mass of a given gas, and in terms of number of moles of gas, you can always write m mu into m0, mu into m0. M equals to mu into m0. M equals to mu into m0. Remembered the formula for number of moles of molecules of a gas? It was mu equals to m upon m0. Then what is capital M? Mu into m0. Mu into m0, correct? What is mu? Number of moles of molecules of a gas. M0 is molecular weight of that gas. Molecular weight of that gas, okay? Now this mu and this mu will get cancelled, giving you finally under root of gamma RT upon M0. Under root of gamma RT upon M0. My dears, in textbook they have written here capital M, but that capital M in the textbook is molecular weight only. Better we should show its symbol using different symbol, different than M. I am putting here M0, okay? So you can clearly distinguish. M means total mass of a given gas, M0 means its a molecular weight, okay? Please remember this formula for the numericals. For a given gas, this gamma is constant, molecular weight is constant, universal gas constant is already constant. So what is the relation between V and T? Come on, from here, V proportional to under root of T. Velocity of sound in air is directly proportional to square root of its absolute temperature, which you must write only in Kelvin. Got it? Fine. Absolute temperature, sometimes it is also called thermodynamic temperature, for your kind knowledge, okay? And now, what does it mean? That V proportional to under root of T means as this temperature will increase, the velocity of sound in air will increase. Now, what is the effect of humidity? Effect of humidity. What is the word here? Humidity is not humanity, which is nowadays nowhere, correct? Humidity, it will give you measure of amount of moisture in air. If amount of moisture in air is more, we say humidity is more. Amount of moisture in air is less, we say humidity is less. Now practically we find that at constant temperature and at constant value of humidity, it so happens that this ratio P upon rho remains constant. Ratio P upon rho remains constant, okay? Because when pressure is increased, density is increased proportionally. When pressure is decreased, density decreases proportionally. In short, this ratio remains constant. Now here gamma is constant, P upon rho, that ratio is also constant. Ultimately, value of velocity of sound in air will remain constant if temperature is constant and if amount of humidity is constant, correct? That's why I am writing here V equals to constant. Now tell me, in rainy season, that is in monsoon, the amount of moist in the air is more. Moist means what? The amount of water vapor molecules. If it is more in air, then that air is said to be having greater moisture. And at that time, in monsoon season, the density of air decreases. Density of moist air is found to be smaller than density of dry air. When this density will decrease in rainy season, then when rho decreases, come on, velocity will increase. Come on, that's why I am writing here, velocity of sound will increase in the monsoon season, correct? When velocity increases, what will happen? You can hear the sound quickly, not louder, but you will hear the sound quickly. Here velocity increases means sound will be heard quickly. If intensity and amplitude are increasing, then you can say sound will be heard louder, but here sound will be heard quicker because velocity is increased, correct? Fine. Now read this statement for illustration number 10. Read it? Come on. What is the relation of velocity of sound with absolute temperature of air? V proportional to under root of capital T. Come on, if it is direct proportionality relation, then when do V1 upon V2 equals to under root of T1 upon T2. Now wait, this first temperature I take it as T degree centigrade, small t degree centigrade. If you want to convert into Kelvin, you will add 273, correct? The second temperature I take it as 0 degree centigrade to Kelvin, you must add 273. 0 plus 273, it is 273 that many Kelvin. At first temperature, the velocity is V1, and because it is at temperature T degree centigrade, I just put the symbol Vt. T you must write well below V, okay? T is here right now, suffix. But mind well, this small t is the temperature value in degree Celsius or degree centigrade. And what about velocity V2? It is the velocity of sound at second temperature, and second temperature is corresponding to 0 degree centigrade. That's why I am putting the symbol V0, correct? Remember, this T is also temperature in degree centigrade, this 0 is also in degree centigrade. Got it? Fine. Put up all these values here. Come on, V1 is Vt, V1 is Vt, correct? V1 is Vt. What about V2? V2 is V0, V2 is V0. This under root of capital T1 is how much? T plus 273, T plus 273. What about capital T2? Capital T2 is 273, capital T2 is 273, correct? Now simplify. Instead of square root, I have taken power 1 by 2, correct? 273 upon 273, this ratio is 1. Plus T upon 273, I am writing separately here, T upon 273. Correct? But tell me, have they given in the statement that T is very much smaller than 273? Yes, they have given. If this is very much smaller than this, then this ratio will be very much smaller than 1. And don't you know expansion of binomial theorem? 1 plus x whole raised to n. 1 plus x whole raised to n, according to binomial expansion, if x is very much less than 1, then what we were doing at the time? We were neglecting higher order terms because they were negligibly small, and we were just retaining only first two terms, which were 1 plus n into x, 1 plus n into x. 1 plus x raised to n equals to 1 plus n into x. 1 plus n into x means what? This into this. And when you make this into this, it will give you t upon 2 into 273. Correct? I repeat. 1 plus x raised to n, when x is very much less than 1, at that time it is 1 plus n into x. 1 plus n into x means this into this, and it will be t upon 2 into 273. Now 2 into 273 comes out to be 546. And now I am writing here nearly equal to, because we are not considering other higher order terms. We are retaining only first two terms, correct? That's why I am writing here nearly equal to. And transfer this V0 in the numerator on right hand side. Then Vt equals to V0, put this value in bracket. Vt equals to V0 into 1 plus t upon 546. Come on, what is this? Formula for finding velocity of sound in air at t degree centigrade in terms of velocity of sound at 0 degree centigrade, correct? Mind well, this small t is not only temperature, but it is temperature to be written only in degree centigrade now. This small t was in degree centigrade, okay, fine. Suppose I take t equal to 1 degree centigrade, just put it here, 1 degree centigrade, correct? And this is V0 means what? Velocity of sound in air at 0 degree centigrade means at STP, just now I told the value, practical value was 332 meter per second. So this V0 is 332 meter per second, this T is right now 1 degree centigrade. Simplify, this answer is 332.61 that many meter per second. Now tell me, this is the value greater than 332. In short, V1 is greater than V0. So let us find out increase in velocity. It will be bigger minus smaller. V1 minus V0 means 332.61 minus V0. V0 is how much? 332, correct? This minus this comes out to be 0.61 that many meter per second. So this gives you increase in velocity of sound in air when you increase the temperature of air at by 1 degree centigrade at 0 degree centigrade. Remember, this increase in velocity depends on the initial temperature of air. Right now, initial temperature of air we had taken 0 degree centigrade. From 0 degree centigrade, if you increase the temperature of air by 1 degree centigrade, then what is corresponding increase in velocity of sound? It is this much, correct? But if the initial temperature is other than 0 degree centigrade, you will have this increase in velocity different than this, okay? So I repeat, increase in velocity of sound in air, it depends on from which initial temperature you are increasing the temperature by 1 degree centigrade, correct? So rate of increase of velocity with the increase in temperature depends on initial temperature, got it? Kindly read this statement of illustration number 11. Read it? Come on, we know V proportional to under root of capital T. V proportional to under root of capital T. Come on, if it is direct proportionality, then V1 upon V2 equals to under root of T1 upon T2. Here you can see these velocities, they do not depend on pressure. They have given two values of pressure just to make you confused. We are not going to use them here. Come on, this first velocity, they have given 345 meter per second. V2 we are looking for. First temperature they have given, when velocity is 345 meter per second, first temperature they have given 27 degree centigrade. Convert it into Kelvin, add 273. What about second temperature? They have given 127 degree centigrade. Convert it into Kelvin, add 273. Now this addition is 300, this addition is 400. Simplify, find out value of V2. Okay, it comes out to be 398.4 meter per second. Okay, wait. This is the value of velocity of sound in air at 127 degrees centigrade temperature. Okay, but they may ask increase in velocity. Then you are supposed to find out V2 minus V1. V2 minus V1. So read the question carefully and then accordingly you try to answer. Okay.